So in a gauge theory, when you pack your gauge fields together, you're missing a bit of crucial information, because between gauge fields we have gauge transformations. So here I draw this picture, and it's one of my favorite pictures, which I put like in all my talks. You put your gauge fields into a collection, into a bag, say, and you have points here. But these points are not independent. I mean, you have additional information in the form of arrows, which describe gauge transformations between different gauge fields. So the mathematical structure this forms is a so-called groupoid, because all those maps are invertible. For each gauge transformation, you can transform back. And the smooth variant of groupoids is that of a stack, and I will talk more about that later on. So in a gauge theory, the gauge fields and their transformations fit into the structure of a groupoid. And this means that being the same is not a property anymore. Because if I give you two gauge fields and I ask you, are they the same? You don't say yes or no, but you have to write down a gauge transformation which connects them. So being the same in such a groupoid is an additional structure, namely that of a gauge transformation between the two gauge fields I gave you. And the important thing is that when moving from this set theoretic world of ordinary field theory to the groupoid world of gauge theory, or even higher groupoid world of higher gauge theory, if you're interested in like higher form gauge fields, you're moving up the categorical ladder. Namely, I didn't catch that. Could you try again? Now my Siri speaks to me. Strange, sorry. So the important thing is that when going from sets to groupoids to higher groupoids, you go up in the categorical ladder. So you get higher categories naturally emerging, because the category of sets is an ordinary one category. Category of groupoids is more. It is a two category, because you have groupoids, maps between groupoids, functors, and maps between those functors, natural transformations. Now, if you move on and you introduce a concept of two groupoids, you would have maps between maps. Sorry. Okay. You see what I mean. You get higher and higher and higher maps, and so you get higher and higher and higher categories. And this goes all the way up to infinity. So if you are interested in the most general framework to describe all possible gauge and higher gauge theories, you should care about infinity groupoids and not about sets. Now, having these higher categorical structures, you have to think about how to formulate them or how to work with them, because you cannot just use ordinary category theory in order to describe these things. So the crucial feature of this higher categorical higher category theory is that it comes with a weaker concept of equivalence. So in a higher category, comparing two objects, you don't do that with the concept of isomorphism, you know, from one category theory, but they are weaker concepts of when you call two things being the same. So for example, when you work with topological spaces up to homotopy, you compare topological spaces up to weak homotopy equivalences. So if you have a map between topological spaces, which induces an isomorphism on all homotopy groups, then you say that this map is an equivalence between these spaces. The same works for simplicial sets. Also, another example you probably know very well is when you work with groupoids, you don't work with isomorphism, but you work with categorical equivalences between groupoids. So a functor in one way, a functor in the other way, such that the compositions are naturally isomorphic to the identity functors. So this is also a weakening of the concept of isomorphism. And probably the most famous one is when you work with chain complexes. The way how you compare chain complexes is again not isomorphism, but quasi-isomorphism. So maps inducing isomorphisms of the homology groups. Now, and the nice mathematical framework in which you can formulate these and study this weaker concept of equivalence is model category theory. So this already showed up yesterday, or in yesterday's talk by Albin, and also in last week's talk. But I want to say a few words a few more details on model category theory and how to work with it. So a model category is a specific kind of category with further structure, which allows you to deal with these concepts of weak equivalences. So a model category is a category C, which is bicomplete, so it has all limits and co-limits. That's a technical condition you need to work with it. And on this category C, you have three distinguished classes of morphisms. So these three distinguished classes of morphisms are called weak equivalences. So that's the main player. So the weak equivalences I denote with such a tilde on top of the arrow. That's the main player, and these are, in our examples, the quasi-isomorphism of chain complexes or the weak homotopy equivalences of topological spaces, etc. So these weak equivalences are the main player. This distinguished class of weak equivalences tells me what are the maps I want to treat as relating objects being the same. Now, in addition to that, you have some additional two classes of maps. These classes of maps are not the main player, I would say, but they are kind of some technical handle you need in order to consistently work with weak equivalences. So these are called fibrations. Fibrations you should think of as maps which are in a very good way surjective. They are as surjective as possible. Where surjective doesn't mean normally surjective, but you should think of that really as something, yeah, like a fiber bundle would be a fibration of topological spaces. Then there is another map, the class of maps, the cofibrations, and these are like as good as injective as possible. And these three classes of maps together have to be compatible. And this compatibility is formulated by a long list of axioms, which I don't want to go into the detail. So when you want to know more about model category theory, of course, there are plenty of books on that subject. But in my opinion, the best introduction to get a bit of a feeling for model category theory is this review paper by Dwyer and Spalinski. So when you Google Dwyer and Spalinski, you will find their review paper. I think it was written for the handbook of homotopy theory or some kind of collected volume of works. And this is really the best short introduction to that subject. So let me give some examples and tell you what one does with model categories and what are the issues. So the examples are topological spaces with weak homotopy equivalences and suitable fibrations and cofibrations form a model category. Simplicial sets with weak homotopy equivalences and suitable fibrations and cofibrations. So the fibrations there are the Kahn fibrations you probably heard about. Groupoid forms a model category. Weak equivalences there are the categorical equivalences, and chain complexes with quasi-isomorphisms forms a model category. So that's quite nice. So the categories and their weak equivalences we had in the examples before, they all form model categories with suitable choices of fibrations and cofibrations and the desired weak equivalences. Now,
I have a question.
Yeah.
In the example groupoids, you say weak equivalences are Morita equivalences, and what are fibrations and, sorry?
Categorical equivalences, so equivalences of categories.
Is it not Morita equivalence?
I think not. I think Morita equivalence is something which appears for Lie groupoids, isn't it?
Yeah.
Here I'm just talking about groupoids in set. So for Lie groupoids,
yeah.
For Lie groupoids, you could take Morita equivalences, and I think that's also model category. No, it's not. I mean, Lie groupoids is to you don't have all limits and co-limits in Lie groupoids, because Lie groupoids have this finite dimensionality restriction. This will not be a model category.
I see. And I wanted to ask you about an example with these fibrations and cofibrations, maybe in groupoid or something else, or on top. I don't know. Maybe you can give an example.
So in chain complexes, it's the easiest. So in chain complexes, the fibrations are the maps which are degree-wise surjective. So they are as surjective as it goes. In groupoids, the vibrations are so-called isovibrations. What that means is, let me see if I can draw a picture. Do I have here some space somewhere? Yeah, let me try to draw here a quick picture. So when you have a functor between groupoids, so let's say G and H, it's a functor between groupoids, and this is called an isovibration. If the following is true, you take an object in G and you apply the functor, and then in H you have an isomorphism. Let me call that H. Yeah. So you apply the functor to an object in G, have an isomorphism there, and the isovibration property is that this comes from applying. There's a map upstairs in the groupoid G, such that applying the functor to F is H. So it's also some lifting kind of property. So vibrations are things which have certain lifting properties. And for topological spaces, examples of vibrations are fiber.
Can you repeat this again? We didn't see it properly. Can you just show again this picture and for groupoid?
For groupoids, okay. Imagine you have a functor. And this functor is a vibration in the model category of groupoids if the following is true. For all objects in the source, you apply the functor, produce an object in H. Yeah? And you take a morphism from some object in H to the image of C under F.
Okay.
So in a groupoid, you just have isomorphisms. Now, it's a vibration if this map here comes from a map in G. So if there exists a map here in G, such that applying the functor you get back your map. So it's some kind of it's some kind of lifting-like property. So these vibrations are like, I think in topological spaces it's easiest to understand. So in topological spaces you have a map from a topological space to another one, and when this is a fiber bundle, you know that you can lift homotopies. Yeah, and this is, I think, how one should think about vibrations. These are maps which are as subjective as possible to allow for lifting of homotopies in a suitable way.
I see. Thank you.
Okay. Where was I? Here. Okay. Now, working with model category theory, it looks scary at the beginning. I have to admit. So it takes a bit time until one gets used to it. But it is, once one gets used to it, it is relatively easy, at least for making your statements. It is easy up to the point when you want to explicitly compute something. And explicitly computing something, this is where you have to put some work in. But there is one aspect in working with model category theory one has to be super careful about. Namely, when you have functors between model categories, so F is now a functor between a model category C and a model category D, these functors are in general not compatible with weak equivalences, which is bad, because functors in one category theory, of course, preserve isomorphisms, but functors in model category theory do not automatically preserve weak equivalences. And that is bad, because we use weak equivalences to compare, to say that two objects are the same. We compare things up to weak equivalence. And if we kind of identify things up to weak equivalence and then apply a functor and get something out which is not weakly equivalent, it's bad. It's an inconsistent. It's an inconsistency. So let me give you an example. Before telling you how to resolve this problem, let me give you an example where this is very easily seen. So push-outs of topological spaces, so gluing topological spaces together. Now here, look at this picture. I take a disk and another disk, two-dimensional disk, say, but this works in n dimension as well, and the circle. The circle maps to the disk by mapping the circle to the boundary of the disk. Yeah, and here the same. Now the push out of topological spaces means you take the two disks and you glue them at the circle, and what you get out is a sphere, of course. Yeah, this is then the northern hemisphere, this is the southern hemisphere, and this is the equator after gluing. Now, this is a push out in topological spaces. It's a certain co-limit in topological spaces. Now, the co-limit functor does not preserve weak equivalences. Why? Because when I work up to homotopy, up to weak equivalence in topological spaces, I can shrink the disk to a point, and I can shrink that disk to a point. Yeah, and these are equivalent as spaces because the disk can be contracted to a point. But if I change this diagram I want to push out now up to weak equivalence into this diagram, and then I push out, I don't get a sphere anymore, but a point. And that is, of course, a bad behavior because, I mean, when you work with spaces up to weak homotopy equivalence and you use ordinary push-outs, then you get inconsistent results here. The point is not the same as the sphere, even up to homotopy. But this is just the kind of thing which is, of course, annoying. It means you have to work a bit more, but you can solve this issue. So this issue that functors do not, in general, preserve weak equivalences can be solved for a large class of functors. And the techniques are called derived functors. So there is a concept of derived functor I will introduce now on the next slide, which solves this problem of functors not preserving weak equivalences. So the situation where derived functors apply to is for so-called Quillnet junctions. This is what I mean by the large class of functors. You cannot derive an arbitrary functor, but you can derive functors which are good enough in the sense that they are part of a Quillnet junction. So a Quillnet junction is a junction between model categories. So F and G are functors. C and D are model categories. F goes from C to D, that's the left adjoint, and G goes from D to C, that's the right adjoint functor. And if you have such an adjunction between model categories, it is called a Quillnet junction if the right adjoint plays well with respect to the model structure in the following sense. The right adjoint preserves vibrations and acyclic vibrations. Acyclic vibrations are maps which are both a vibration and a weak equivalence. The model category axioms are so strong that you have an equivalent dual perspective on that, and it is equivalent to say that the left adjoint functor preserves cofibrations and acyclic cofibrations. So these two things are equivalent conditions. Right adjoint functor preserves vibrations and acyclic vibrations, or vice versa. Left adjoint functor preserves cofibrations and acyclic cofibrations.
And to be adjoint, does it mean that if you compose the two, you get something like a natural equivalence to the identity or something? If yes, you compose F and G?
Adjoint functor means that you have a unit and a co-unit. So when you go first left adjoint, then right adjoint, and you can compare that to the identity functor, and you want to have a unit of this adjunction, and you can go first right, then left, and you compare that to the identity functor. So this is now the identity functor on C, this is the identity functor on D, this is the co-unit, unit, co-unit, and these satisfy triangle relations. So an adjunction is not as strong as an equivalence of categories, but it is a way how to relate the categories. You have functors in both ways, and doing the compositions going back and forth and back, you can compare to the identity functors, but these don't have to be natural isomorphisms. The unit and co-unit can be just natural transformations. And there is an equivalent perspective on adjunctions, which is that when you look at the maps in the category from the left adjoint on an object to another object, so this is now the maps in D, you want these Hom sets to be bijective in a natural way to Hom in C from C to G of D. So these are equivalent definitions of adjunction. So this Hom set version tells you that that mapping out of the left adjoint applied to an object is the same as mapping into the right adjoint on an object. So these are two equivalent ways of saying what is in a junction. Many constructions are junctions in real life. So for example, the limit functor is a right adjoint, the co-limit functor is a left adjoint, the free algebra is a left adjoint, etc., etc. So a lot of functors in nature are part of an adjunction. So this
Thank you very much.
Not too restrictive. Now, Quillen adjunction is a bit more restrictive because you want to have an adjunction together with the property that the right adjoint preserves part of the model structure. But the nice thing is when you have this Quillen adjunction, is that you can produce functors which are compatible with weak equivalences. So how does that work? This is the theorem here, which is, I think, one of the main theorems of model category theory. It tells you that for every Quillen adjunction, Fg, you can define a left-derived functor, which looks as follows. So the left-derived functor is with this funny L. Lf is the left-derived functor, and you get it by composing. You first do a cofibrant replacement. So you replace your object by a fatter one, which is a cofibrant object, and then apply the functor. So this is again a functor from C to D like F, but this functor is better because it preserves weak equivalences. And you can also define a right-derived functor, Rg, you get by precomposing G with a fibrant replacement functor. Okay, so these things are nice. They exist always in model category theory. So when you have a model category, when you have a Quillen adjunction, you have these derived functors. But I have to tell you the kind of dirty detail is that, okay, you can now do arguments with derived functors, but you have it's hard in general to compute these cofibrant replacements and these fibrant replacements. So even though you know that these derived functors exist by abstract nonsense in model category theory, the main challenge when working in such a framework is to find really formulas or models for computing these derived functors. So I will show you an example later. I think on Thursday. Okay, now after this quick intro to model category theory, I want to ask the question: does one really need all this jumbo? Yeah?
What does it mean to have a cofibrant replacement, and what would it be in the example with the disks?
In the example with the disk, it is fine. So a cofibration. Think of a cofibration as something which is very nicely injective. Now you see that this diagram here has this feature because these two arrows here, they are very nicely injective because the circle maps nicely injectively to the boundary of the disk. But after I shrink the disk to a point, this map from the circle to the point is far away from being nicely injective. So when I would like to compute the derived pushout, which is called the homotopy pushout of this diagram, how would I compute it? I would fatten up the point in such a way that these arrows here are cofibrations, are nicely injective. And the way how to do it is I expand the point to the disk. And so this is the main idea behind these derived functors. So you apply them to your object, but not directly to the object. You replace your object by a weakly equivalent fatter one, which has this cofibrancy property. And yeah, for this disk example, it would mean expand the point to a disk and then compute the normal functor on that. And
thank you. That's very illustrative. Thank you.
Yeah. And in general, maybe I should add that quickly. So in general, so these cofibrant resolutions. So this is a functor from C to C. And you also want to, with the property that whatever I feed in, it spits out a cofibrant object. And I want to compare these functors also to my original object. So now I have to think about which way it goes. Does it go this way? I think so. Fiber resolution. Yeah. So it also should come with a natural weak equivalent. So cofibrant replacement functor means not just take one object and fatten it up to be a cofibrant object, but also naturally comparing it to the object you fatten up. So I didn't want to go too much into the details, but yeah. So okay, when this was confusing, forget it. So does one really need all this mumbo jumbo in order to do gauge theory? And I think yes, I think one needs it. And I want to give you an example where derived functors really are important for a gauge theoretic problem. So imagine we want to do gauge fields with structure group G on a Cartesian space. So let's start very easy. Now on a Cartesian space, we know very well what is the groupoid of gauge fields with structure group G. It's simply the groupoid whose objects are the gauge potentials. So these are the connections, and because we have a Cartesian space, there are no non-trivial bundles. So everything lives on the trivial bundle, and we have the gauge fields are just one forms with values in the Lie algebra. And the morphisms of this groupoid are gauge transformations. So they go from a gauge field to a gauge transformed gauge field coming from this usual formula. And this G is, of course, a group valued function. This is how you do gauge transformation. Now with this definition, I now kind of declared what I know about gauge fields on Cartesian spaces. And you might now wonder, is it possible to deduce from this definition what are gauge fields on generic manifolds? And my claim is that speaking this model category language or the higher categorical language, you know that automatically. This is everything you have to know about gauge fields. You just have to know them on contractibles because they satisfy the descent condition. So how does this work in practice, and how does this relate to derived functors? So now assume I take any manifold, yeah? M. M can be any manifold, not necessarily a Cartesian space. And take a good open cover of this manifold, Ui. Now, for each patch Ui and for each overlap Uij, these are all Cartesian spaces. So you know already what are the gauge fields on these. So I can take the groupoid of gauge fields on the patch, take the product over all possible patches. I can take the groupoid of gauge fields on the intersection, take the product over all possible intersections, triple intersections, etc. So I can build these objects here, and then I have always two ways of how to restrict to intersections, isn't it? So from Ui, I can restrict to Uij, from to Uij, I can restrict from Ui and from Uj. Yeah. So Ui, Uj, both restrict to Uij. Sorry. I'm already thinking dual. Sorry. Uij sits in both Ui and Uj. Now, restricting gauge fields, you can pull back forms. You get these two arrows here, yeah, corresponding to the two different ways how to embed the overlap, once in Ui and once in Uj. And here similarly for the higher overlaps. So this diagram here I draw tells you the gauge fields on all these patches and intersections and the way how you restrict them. Now, this is all the information you need, is my claim. But it goes wrong if you don't buy into the derived functors. So if you want to glue now this data by using an ordinary limit, which is not a derived functor, which is not compatible with weak equivalences, you will see the following. Computing the limit of this diagram, so how does the limit work? You take an object in here, so family of gauge fields on each patches, such that the two ways how you can map to there coincide. So this gives a kind of condition that the AI has to coincide with AJ on the overlap, so you get a global A. And the morphisms are similar. A family of morphisms on Ui agreeing on the overlaps gives you a globally defined morphism. So what you see is when gluing these data using an ordinary limit instead of a derived functor, you don't find non-trivial bundles on your manifold. But this is solved when you remember that you're doing something illegal here. The ordinary limit is not playing well with respect to equivalences. So let's do the correct limit. Let's do the homotopy limit. So the homotopy limit is a derived functor, so the right derived functor of the limit functor. And if you compute the homotopy limit, and there you can work out formulas how to compute it, you get this thing. Now, I talk you through this groupoid here, and I tell you then how it comes from this diagram, what happens then in this diagram. So what you get out is the homotopy limit is the gauge potential on each patch, together with the transition function on each overlap, satisfying the condition that the gauge potential Aj coincides with Ai on the overlap up to the gauge transformation Gij, and these Gij satisfy the co-cycle condition on triple overlaps. So this is clearly kind of Czech description of bundles you find here. And the morphisms are locally defined gauge transformations on each patch Ui. And they go from Ai Gij to Ai gauge transformed and Gij adjoint transformed. So in this groupoid here, when you compute it with the correct derived functor, knows all bundles. So of course, now you might say, but I know all bundles, so why do I need model categories? I'm just saying that even if you wouldn't know all bundles, yeah.
So more generally, what does limit and homotopy limit mean? So why in this case it gives the gauge transformations, which is evidently very nice. But what was the general definition that applied to here? You get the gauge transformations.
Yeah. So limit here in this special case means equalizer. So how would you compute this normal limit? Let me first say how to compute the normal. So limit is a categorical construction. Limit is a way how to approximate a diagram by a single object. But let me better explain it at this example for these equalizer things. So if you would have if these wouldn't be groupoids, if these would be sets, you would compute the limit as follows: take an object in here, and apply these two maps, and just take the objects in here, which under application of the two maps go to the same map here. So it's like a kernel. It's like a kernel. The kernel would be a single map, and you compare it to 0. So when one of those would be the 0 map, it's a kernel. So you take objects in here, satisfying the condition that they map to the same here. And this is why we get here global gauge potentials. Here you have locally defined gauge potentials, such that the restrictions coincide, which means that it is a globally defined form. Now, the homotopy limit does something different. The homotopy limit says, take an object in here, which is a family of gauge potentials, such that between the two arrows you have here, the result agrees. But what means agreeing in groupoids? In groupoids, agreeing means that there's a gauge transformation between those two. So taking a family of gauge potentials, restricting them to the overlaps, you get agreeing gauge potentials, but agreeing means there's a gauge transformation. And this is the Gij. So these transition functions are the witnesses telling you that restricting Ai and Aj to the overlap, they agree. But remember, being the same in a groupoid is not a property, but it's a structure.
Okay, very good. And I suppose limit means, like in the first case already, that it continues like this. So the first element is like all elements which are mapped to the same with the two arrows, and then it continues like this, I suppose, right? With the 3 arrows and so on.
Yeah, here you don't see deeper. I mean, ordinary category theory just sees until here, and groupoids see until here. And note that on these triple overlaps, this is where you get then the co-cycle condition. So in this homotopy limit, the triple overlaps play a role. This is where the co-cycle conditions live.
I see. Thank you.
Okay, so in principle, a homotopy limit is just adapting the concept of limit, take things which coincide after mapping, and now coinciding or being the same is witnessed by a gauge transformation. So this is what the homotopy limit describes correctly. Okay, now let me quickly talk a bit about stacks. So stacks are, so we had stacks before. I think Albert was talking about stacks yesterday. I want to just tell you, I won't give you full definitions, but I want to kind of tell you what they are and how to think about them in a looser way. So we talked about groupoids. We talked about groupoids, but groupoid is of course not enough. I mean, it's like groupoid is the analog of a set. We don't have a smooth structure of that. So a set relates to okay, let me say it better. So we would like to have groupoids with a bit of smooth structure on them. Why? Because when you want to do field theory, you want to do like smooth functions on these groupoids, or you want to do differential forms on these groupoids, etc. So you want smooth groupoids. Now you can take Lie groupoids if you want, but this doesn't help you very much in field theory because these groupoids are infinite dimensional in field theory. So Lie groupoids will not be sufficient. So we need something more general, and this is the concept of stacks. So stacks is a quite general class of smooth spaces or smooth groupoids, which is useful for describing gauge theories. Now, without going into the details, a stack you should think of as in its functor of points perspective. So a stack you describe by functor, by presheaf with values in groupoid. So it goes from manifolds to groupoids. And it satisfies the suitable descent condition, which is derived in the sense that it has homotopy limits involved. Now, independently on how to define that precisely, how you should think of this presheaf is as follows. It's as a functor of points. So the points of the field space of gauge theories are a groupoid. And how to get these points from the stack perspective is that you take your functor of points and you evaluate it on the point. Now, how you should think of this, evaluating the functor of points on R0 on the point, is that's the groupoid of points of my stack. So how to picture it is, here's the point, and I look at all possible ways how to map the point to the stack, and I see now the groupoid corresponding to the points of that stack. But the stack knows more. The stack knows also the smooth curves. And these smooth curves, again, form a groupoid because yeah, there are gauge transformations also between smooth curves. And you go on. You have smooth planes in the stack, and this you get from evaluating your functor on R2 and so on. So this presheaf encodes how to map test spaces into your smooth space, into your smooth stack.
I'm not sure, and I'm not sure I understood it. So this X is a functor or what?
X is a functor.
And if R0 is just one point, it's one particular map or what? So no. You said all possible maps. So that confuses me.
Yeah, exactly. So the X is a functor, and I can evaluate it on manifolds and think of these manifolds as test spaces. Now, when I evaluate X on the point, which is a zero-dimensional manifold, I get a groupoid because this is what the functor spits out. And this groupoid is the groupoid of points of my stack. Like in the gauge theory example is down there. We'll talk you through that in a moment. So the group of all points. So you don't get just one point, but it's a collection of many points. So of all possible points. Because what this X on R0 describes is all possible ways how to map R0 into X, and you can have that.
And all points are connected by morphisms in the target node.
No, not necessarily. I mean,
some groupoid or what?
Some groupoid. I tell you now the gauge theory example, then this becomes, I hope, super clear.
Excuse me, can I ask another question?
Sure.
It says x of R2 is the groupoid of all smooth planes in X.
Yeah.
Is it all surfaces in X?
Yeah, surfaces. I think I wrote that too quick. I mean, this is always all the possible ways how to smoothly map R2 into X.
And how should I then think of, for example, a genus 7 surface? What is the image of a genus 7?
Then you have to take another test space. You can evaluate the functor on all test spaces you want. When I evaluate, for example, X on S1, then this is the groupoid of all loops in here. And when I evaluate X on another surface, like a genus 8 surface, then I get like that in here. So all possible ways how to map one guy into the other guy. So you should think of the argument of the functor of points as the type of test space you use to probe your space. And that is really a nice way, because manifolds are super restrictive, because for manifolds you use charts. And this kind of gives you a restriction how high dimensional you can go. While this functor of points perspective, you probe your space by kind of probing it against all possible test spaces. And that is sufficient to do many things in differential geometry. So you know what are tangent vectors, you know what are forms using this language. So it's like instead of describing a space by putting charts on it, this functor of points tells you describe a space and its smooth structure by telling you how all test spaces map into it.
Is it true that there's some kind of redundancy in a stack then? Because if I describe a surface in terms of charts made up of R2, then
that's the descent condition, exactly.
Right. Uh-huh.
When you evaluate your stack on a manifold, you can also evaluate it on a cover of the manifold, include the results. So this is the descent condition. It's like a sheaf condition, but a sheaf condition where you replace the limits by homotopy limits in order to get the gauge theoretic gluing right.
Mm-hmm. Thanks a lot.
So I hope that this example now clarifies that. So this is the stack of gauge fields with structure group G. And I just look at in order to kind of avoid cumbersome notation involving bundles and so on, I tell you the stack, so the smooth groupoid of gauge fields with structure group G on a Cartesian space only. So a stack, we said, is a functor from manifolds, a contravariant functor from manifolds to groupoids. So if I take now a manifold N, what does this functor assign? It should assign something which I can interpret as N-shaped curves in the space of gauge fields. And this is formalizing that. So the objects of this groupoid I assign are one forms on U times N. But, okay, U is my spacetime and N is my test space. And I take forms which just have legs along spacetime. So this you can think about as smoothly N parametrized, because there are no legs on N. So it's just N appears here to smoothly parametrize your gauge fields. So this is like a smooth family of gauge fields parametrized by N. And the same for the morphism. So a morphism is now a gauge transformation where the differential here just operates on the space-time part. So it's this kind of vertical differential. And the gauge transformation is also smoothly parameterized. So it's a gauge transformation for each point in N, but it depends in a smooth way. So these stacks of gauge fields are just the points of shape N are just the smoothly parameterized gauge fields. And how does this relate to the groupoid example I had before? So if you now take the points of that, so you forget the smooth structure, you just look at the points of this stack. So you evaluate it at R0 at the point, then this goes away, and this goes away, and you end up with the groupoid of gauge fields we had before. And when you evaluate it on the line, for example, you get the smooth curves in the groupoid of gauge fields, etc. And so this is how the stack records smoothness, by telling you what are smooth maps into it. Now this is, I think, what I wanted to say about stacks. So now I want to move on and say a bit about quantum gauge theory. But before passing over to quantum gauge theory, we have to do something, because in a quantum field theory we want to describe the observables of the system. And so far I just described the space or stack of field configurations. And observables, classically, so before quantization, should be certain functions on the space of field configurations. And we have to kind of generalize this idea of taking functions from spaces to stacks. And this is what I want to do here very briefly. So there is a nice concept of function algebra on a stack. This is then not an ordinary algebra, but a differential graded algebra. And that is mimicking very, very much what you know how to assign to a simplicial set or topological space. It's normalized cochains. When you have a topological space, you can assign its normalized cochains. And the same works for a simplicial set. These normalized cochains, they come with a product, and this product is commutative up to homotopy. So to a simplicial set, you can assign a commutative up to homotopy algebra, so an E-infinity algebra in chain complexes, which you can think of as a kind of function algebra on the simplicial set. Now, this construction here, forming normalized cochains without digging into the details, this generalizes to stacks and even more to infinity stacks. So infinity stacks are like stacks, but here groupoid is replaced by infinity groupoid, and infinity groupoids you can nicely describe by Kahn simplicial sets. So
Alexander,
yeah.
Can you go one page more?
Yeah.
At least some of us probably don't, me included, don't know what this alg infinity is. Could you just explain it in a very simple, simplicial set, like a triple or something?
You mean the infinity algebras or this?
No, this one which you this functor which you were talking about.
Okay.
For some simplicial set.
I have an example down there. I will tell you the example in a second, and then let's see if, okay, I tell you the example and then let's see if you're happy with. So this assigning normalized cochain algebras generalizes to stacks and infinity stacks. So infinity stacks are like stacks, however, with groupoids replaced by simplicial sets, and you get a left Quillen functor assigning to a stack its function differential graded algebra. And these function differential graded algebras are commutative, not strictly, but up to homotopy, so E infinity. So let me tell you the examples and then maybe going into the details how this is defined, which I wanted to avoid, but maybe I cannot avoid. So when you have a manifold is a stack, a very simple one which doesn't have arrows, so where the groupoids of points are just sets, because on a manifold you don't have gauge transformations. Now, if you feed in a manifold in this construction, this functor spits out the usual smooth, the algebra of smooth functions, which is a strictly commutative differential graded algebra with trivial differential. Now, if you have a more complicated stack, namely a Lie algebroid, here I just take this action Lie algebroid, so you have a manifold Y, and you quotient out a Lie algebra action. So this means take the action Lie algebroid, and then you take on this Lie algebroid, this function E infinity algebra, you will get the Chevalier-Eilenberg algebra, cochain algebra of this Lie algebra with values in the smooth functions on the manifold you quotient out your Lie algebra action. And when you take a Lie groupoid, which is a simple example of a stack, so here the action Lie groupoid, I take Y a manifold, G a Lie group, then this concept of function algebra gives you the group cochain algebra of the group G with values in the smooth functions on Y. So so should I say something more generically about this guy, how it is defined? Thomas? So what this thing does is
so in the case of Lie algebroids, I suppose this description just reproduces the picture of vein drop, right? As a DG or Q manifold. Is it true?
For Lie algebroid. For Lie algebroids, you get the Chevalier-Eilenberg differential graded algebras, which I think is the dual language for Q manifolds, isn't it?
I suppose so, yeah. Mm-hmm.
Yeah.
Mm-hmm.
Exactly. So
and how do you get this by the definition, like just in this example, for example? What is the definition of this? Or if it's too complicated, you drop it. But can you explain?
So here the kind of trick is the following. So how this relates to simplicial sets. When I have a functor with values in groupoids, I can take the nerve of the groupoid and end up with a simplicial set. Now, on a simplicial set, I have these many maps, and when I take the free abelian group generated by a simplicial set and take alternating sums of these maps, I get a chain complex. Quotienting out some stuff, I get a normalized chain complex. So this is the normalized chain complex associated with the simplicial set. Now, what this construction does is simply take the simplicial set, make the free abelian group, alternating some of these phase maps to produce a chain complex, and then dualize it. So this is what this construction here does. And the construction at the level of stacks does that for each the functor of points. It does it kind of for each test space separately. So it does it point-wise, object-wise for these functor of points. So it's a quite standard construction, which you.
I see. Okay, I got some idea. Mm-hmm, thank you.
So I want to give you a quick warning, which because this I feel that this is a point which people don't emphasize often enough. So here this construction, whatever are the details, is a way how to assign to an infinity stack an E-infinity algebra of functions. So a commutative up to homotopy differential graded algebra of functions, which is nice. So this is the first step to pass over to observables of a field theory. But the issue is that this function algebra does not, in general, encode the stack faithfully. So, and there's a very simple example. When you take a point and you quotient out Z2, so this is an example of a quotient stack, as Albin introduced it yesterday. And this quotient stack has a name. It's a classifying stack of Z2 bundles. And now I might ask, what happens when I take functions, a function DG algebra on this classifying stack of Z2 bundles? And you find that this is the trivial algebra, which is the same as the algebra of the point. So all the information about the Z2 action, so this is a very simple model. There's one gauge field with a Z2 gauge symmetry. So in physics terms. So here I totally forget about the gauge symmetry when I pass over to function algebras. This is what I mean, that the function algebra does not encode the stack faithfully in general. And this is a well-known result, which of course people in algebraic geometry have seen years ago and know how to deal with that issue. This problem, just to ensure you that it's not too bad for physics purposes, this problem is associated to finite gauge transformations. So infinitesimal gauge transformations, in the sense of Lie algebroids, they work very well. Then these function algebras are no problem. They are faithfully encoding the Lie algebroid. But for finite gauge transformations where you break out of the Lie algebroid picture, so you go to something like that, to Lie groupoid, you can run into issues that your function algebra doesn't remember your stack faithfully. Now, what people do in algebraic geometry, which is also what we try to do a bit in algebraic quantum field theory, is instead of assigning these function algebras to stacks, one assigns so-called quasi-current sheaf categories. So Albin already mentioned that yesterday, but let me tell you the picture behind that. So on a space, you can take functions, or on a space, you can take all possible vector bundles. Now, when you have a normal space, like a manifold, of course, the function algebra knows the manifold, And the category of vector bundle knows the function algebra because there's the trivial bundle, and when you take its sections, then you get your algebra or functions back. But stacks in general can be a bit more complicated, that they're not fully encoded by their function algebra, but that you have to study also generic vector bundles on that stack. And these are recorded in these quasi-coherent sheaf categories. And then there is a theorem by Lurie, which tells you that you can reconstruct from these quasi-coherent sheaf categories a large class of stacks. And this is the point of view which people in derived algebraic geometry take. So Kalak, Pandev, Toen, Marquis, Vezzosi, they don't assign function algebras and quantize them, but they assign quasi-coherent sheaf categories and quantize them. And in a recent paper, we did some similar things in the context of AQFT, but I'm not going into the details here because this is a bit more complicated. Okay, now I'm almost out of time and I didn't say anything about homotopy AQFTs. So let me quickly say a bit about that. So I hope that this discussion, which was unexpectedly lengthy, unfortunately, motivates that it makes sense to look at AQFTs with values in chain complexes. And to look at these AQFTs with values in chain complexes in order to describe quantum gauge theories in terms of quantized function algebras on stacks. So these function algebras are DG algebras, that's why we look at chain complexes. Now here is the small problem that these non-perturbative features coming from finite group actions might get lost in this description, but working with chain complexes is kind of considerably easier than working with these quasi-coherent sheaf categories. Now, how to do AQFT with values in chain complexes is quite easy when you follow this operatic approach, which I told you about in the first lecture. Namely, the operatic approach, you had the choice of a target category. It just had to be a symmetric monoidal category. And chain complexes are a symmetric monoidal category. You can take tensor products of chain complexes and swap them up to signs. So we can easily define a category of, I call it strict chain valued AQFTs on an orthogonal category, so on a spacetime category. And this is a category of algebras over the AQFT operand, however, with values in category of chain complexes. So strict AQFTs are algebras over the AQFT operand with values in chain complexes. Now there are plenty of models for that, plenty of examples. So all the models which Klaus and Kasha are constructing in this perturbative PV formalism define strict AQFTs in this strict chain valued AQFTs in that sense on the category of Lorentzian spacetimes log. Now, a kind of important piece of information about this category is that this is a model category. So the strict AQFTs on every orthogonal category is a model category. And here the weak equivalences, vibrations, and co-vibrations are as follows. So the weak equivalences are nice. So these are maps between AQFTs. So remember, AQFTs are like functors. So these are natural transformations. And the natural transformation is a weak equivalence if all components are quasi-isos. So this is the weak equivalences in this model structure on strict AQFT. And the vibrations are natural transformations such that all components are degree-wise surjective, and the co-vibrations are determined by a certain lifting property, which I don't want to go into the details. So what is important here, as emphasized before, the weak equivalences are the main player. So here this model category structure tells you that when you work with gauge theoretic AQFTs, you have a nice concept of weak equivalences, which behaves well, and which is also the kind of obvious one, namely the one where you have component-wise quasi-isos. And this concept of weak equivalences you can use to compare gauge theoretic AQFTs. I'm really running out of time. So now, just very briefly. So whenever there is a strict algebraic structure, there are kind of homotopy coherent analogs of that. So for example, when you study associative algebras, you can also move on a bit and study infinity algebras as algebras where associativity is not strict, but up to coherent homotopy. When you study Lie algebras, then maybe at some point you study infinity algebras where the Lie algebra relations are just up to coherent homotopy. And now the question is, now we studied AQFTs with values in chain complexes. Is there such a homotopy coherent version which compares like L infinity algebra compares to Lie algebra? And indeed there is, and this is also important because many constructions one can think about will not directly give strict AQFTs. So for example, when you take function algebras on stacks, you get E infinity algebras, which are not strictly commutative, but just commutative up to coherent homotopy. And how to define these homotopy coherent algebraic notions is, again, Oprah theory tells us exactly what to do. And the key point here is that of resolutions of Oprah. So the homotopy versions of algebraic structures are coming from fattening up in a certain way your operands. And these resolutions are called sigma cofibrant resolutions. But since I'm already over time, I don't want to go into the details. So I just say that there is a standard concept of resolution for operands called sigma cofibrant resolution. And this is what gives you here in all these cases the A infinity, L infinity, and also the AQFT infinity algebras. So the definition is now relatively straightforward. So applying this concept of resolution to the chain complex valued AQFTs, you introduce a category of homotopy coherent AQFTs, which is also a model category, where some of the properties like Einstein causality and time slice are not strict, but just up to coherent homotopy. And you can produce examples, which I will skip because I wanted to say something more important. So I skip the example, but I tell you that these homotopy coherent AQFTs have a strictification theorem, like L infinity algebras can always be strictified in characteristic 0 to Lie algebras. Also, these homotopy AQFTs can be strictified to strict AQFT, and this is the content of this strictification in characteristic 0. Now, application. I want to show you again so this is promised, the last one, and then I'm stopping. So I want to show you one more example where you see that derived functors are really, really useful for doing funny things in gauge theory. So remember from yesterday's lecture that a functor between orthogonal categories gives you an adjunction between AQFT categories. So this, for example, extension restriction adjunction, which we had. Now, in the world of model category theory, we have a nice result that every orthogonal functor gives you a Quillen adjunction, which means we can work with it because the Quillen adjunctions are precisely the ones one needs in order to construct derived functors. Now, what that means is that when you, for example, look at the problem where you want to extend from topologically trivial spacetimes to all spacetimes, your AQFTs, you get a derived extension functor from these techniques. So you can take a gauge theory on contractible spacetimes and produce by this derived extension functor a gauge theory on all spacetimes. So that is again similar to factorization homology in the context of topological QFT. And I show you one toy model where this kind of illustrates how powerful such an extension is in a super simple toy model. So I'm not talking about Lorentzian manifolds now, but just super simple toy model. I take as categories disks, two-dimensional disks, oriented, and two-dimensional manifolds, oriented. Of course, disks are a subcategory of manifolds. Those disks are specifically manifolds. And I take the orthogonality relation, which kind of tells me the commutative behavior, the maximal one. So every pair of map is orthogonal. What this means is that I'm looking at theories which are not quantum. They don't have non-commutativity inside. So this you can think of as toy models which are not quantized. Now, in this situation, we have one of those derived extension functors, which extends theories from disks into manifolds. And this extension functor for this maximal orthogonality relation tells us, okay, AQFTs on here are just functors to E infinity algebras. So as I said, there's no quantum, so everybody commutes. Let's take a toy model and see what happens. So I give you now a very simple toy model of a theory on disks. And I say the following: it's the functor which assigns to disk U the free E infinity algebra with one generator in degree -1. This one generator lives in degree -1. So from a field theoretic perspective, you should. I have to say I use chain convention. So in degree -1 means that this generator is a ghost field. So I look at the field theory, which is nothing else but a theory with one ghost field, which is even constant. Yeah, a super simple field theory. It has no fields. It has just one ghost, which is constant. And this is the observable algebra for this theory. And now I might ask, what happens when I compute the derived extension functor? And this is really super easy. I mean, just one ghost field and it's constant. When I compute the derived extension functor, I see something which looks pretty rich, or relatively rich. Namely, when you extend it to a manifold, this one ghost field glues together in a funny way to produce the E infinity algebra generated by the compact de Rham complex on your manifold. And this has a field theoretic interpretation, because when you have Chern-Simon theory, linear Chern-Simon theory, and you look at it on a slice, on a two-dimensional slice, then these are exactly the observables, unquantized, of linear Chern-Simon theory. So from a stupid theory on disks, which just have a constant ghost field, you can get by these derived extensions a quite rich theory on two manifolds, namely unquantized linear Chern-Simons. Okay, I already went so much over time. Quick summary. Higher categorical structures in classical gauge theory are because of the groupoid and stack structure of gauge fields and the gauge transformations. So this I think I explained in quite some detail. Model category theory is a quite concrete framework to work with such higher categorical structures. You can use also higher categories or infinity categories, but I find them harder to work with. Now, in quantum gauge theory, these higher categorical structures are also present, and they come in the form of differential graded algebras of observables, for example, as those appearing in the BV formalism. Now, at the level of AQFTs, we have developed model categories for strict and homotopy coherent AQFTs, and realized that all our universal constructions from the last lecture are, in fact, can be derived. So they are derived functors for these universal constructions. And especially the derived local to global extensions are very interesting and rich. So because you can get, as an example, quantized linear Chern-Simons on a two-surface from a super stupid theory on disks, which is just describing a single constant ghost field and no other fields. Okay, thanks a lot, and sorry for going over time.
Okay, we have time only for short questions, maybe first online, if there is one. Just unmute yourself and ask.
I have one again. Thanks a lot for these lectures. My most pressing question is how this connects to Dijkgraaf-Witten theory. So, right. So I guess the last example must connect to that, but more specifically, it's widely expected that Dijkgraaf-Witten theory is a fully extended TQFT. So you can discuss it in language very similar to the one that you're using. On the other hand, you describe gauge theories for not necessarily discrete gauge groups. Dijkgraaf-Witten is for discrete gauge groups. So can you see how you get an extended, maybe twisted Dijkgraaf-Witten theory as a special example of the theory that you're describing?
Yeah, this is a good question indeed, and I was thinking about that. So we this paper about these operat and homotopy techniques I wrote with Lukas Voige, who was a PhD student of Schweigert, and he has this topological field theory experience. But we couldn't make a precise link to what people do in Dijkgraaf-Witten and other topological field theories. So it's I don't understand much about topological field theory, unfortunately. But there is you can do other examples of that type where you have a discrete group as an input, then you do the derived extension, and then you see then you see the non-trivial bundles popping up like in Dijkgraaf-Witten theory. But a concrete relationship between that and the topological field theory description we've never seen.
Mm-hmm. Okay, thanks. Maybe we can discuss this another time. If I may, a very quick question, just on a technical level. If I remember correctly, there's more than one equivalence class of model structures on chain complexes.
Yeah.
So which one is the one that is relevant here, and why?
So I work on unbounded chain complexes. Unbounded chain complexes have a projective and an injective model structure. And it is just the projective one which is compatible with the tensor product, because you want the tensor product to be compatible with quasi-isors. And so I work with the projective model structure, because this is the one where you have a tensor product and where the chain complexes are a so-called symmetric monoidal model category.
Oh, I see. So unbounded chain complexes, there's not 5 model structures, but only 2?
I think there might be more even, but they are yeah, good question. I mean, I just know 2 from. Okay, let's say in the pre-Emily Riehl time there were 2. In these older
Exactly.
theory books, they just have 2. But I think Emily Riehl found some more, but I didn't look into them. So this projective model structure is the one which is very useful, because this also then connects nicely to model structures for operats, and this is in papers by Vladimir Hinich and also Benoit Fraisse and so on. Days when you want to connect the chain complex model structures to operats, there is this distinguished choice. I think distinguished choice.
I see. Thank you.